Good afternoon, ladies and gentlemen. It's Marco Amato from the Czech Technical University, Faculty Civil Engineering Department of Mechanics. So Marco did his master and then he moved to the University of Trento, and he was a PhD student of Professor Davide Bigoni. He got PhD last year in 2024.
Yeah, exactly.
And then he moved to Prague, and he is now in the group of Martin Horan at the Department of Mechanics, so the Faculty of Civil Engineering. So actual mechanics, and I think he will tell us something about his PhD in this. So Marco, welcome.
Thank you very much. Thank you very much. So yes, I thank you very much for this introduction, and I'm here to show you my research work, actually my PhD studies, titled Elastic Solids Under Frictionless Rigid Contact and Configurational Force, done at the University of Trento under the supervision of Professor Bigoni and Professor. It's fundamental to start from Hesselby. Why? Because Hesselby actually was a pioneer of configuration mechanics. And he introduced the concept of analysis of energy. And basically what did he do? It was to compute the total potential energy stored in the material. Then, by keeping into account the defect position, he was able to define the configurational force as minus the first derivative of the total potential energy with respect to the defect position. In the particular case of rectilinear crack, Jim Rice found that the energy release rate associated with the advancement of the crack tip is equal to a very particular kind of integral, the so-called J integral, J in his honor. And it is also possible to show that this integral is path independent, and it involves the Hesselby energy momentum tensor P, which contains the strain energy density function, the displacement gradient, and the Cauchy stress tensor. So, knowing all these ingredients, we can finally express explicitly the J integral, and please let me allow to highlight the fact that this integral is path independent. So that means that it doesn't change its values while changing the counterclockwise path integration gamma, and it is a configurational force. And it is also a configurational force. Then, Bigoni and his research group extend the concept of configurational mechanics for a very particular class of elastic structure, the elastic structure characterized by a variable length. And this variable length was made possible by considering this particular constraint, which is the sliding sleeve. So the sliding sleeve basically allows the elastic rod to freely slide inside it, but it prevents the transversal displacement and the rotation. So considering now a dead load applied to the free end of the rod, a configurational force arises, where at the sliding sleeve exit there. And this configurational force was shown to be proportional to the reaction moment m, the bending stiffness B, as minus m squared over 2b. And this configurational force was measured also with experimental tests in both statics, but also dynamic regime, where on the left we have the free fall dynamics and the sliding sleeve is fixed, while on the right we have the stabilization and self-tuning from a sliding sleeve oscillation. So far, configurational forces were thought to be different in nature from the classical Newtonian forces that arise as an example in the equation of motion. And this is why Ballerini and Royer Carfagni, inspired by Bigoni's result, they was looking for a Newtonian interpretation for this kind of forces in two particular kind of defects, the edge dislocation and the crack propagation. And they were able to find this kind of interpretation by considering simplifying model for this kind of defects. Again, the edge dislocation and crack propagation and the defector studies are represented here in this slide. Along this research line, the goal of my thesis was to further extend the concept of configurational force in the case when an elastic solid indented by undergoes large deformation when indented by a frictionless flat and rigid punch. What we expect? We expect a configurational force arising in the corner of the punch, And we expect also this configurational force being equal to the energy release rate associated to a growth of the rigid punch, also equal to the J integral where performed around the corner of the punch, but also equal to minus the horizontal component of the contact reaction force. And in order to do that, let us start from an accidental coincidence in linear elasticity. So we consider a linear elastic hull space indented by a frictionless flat rigid punch. Then we focus our attention on the right corner. And as we know, a singular stress state arises there. But by using an asymptotic approach, we are still able to write the stress component, here reported in polar coordinate and in function of K1, which is the stress intensity factor, the same stress intensity factor that arises in mode 1 crack propagation. And still, by using asymptotic approach, it's also possible to define the normal displacement arising in the free surface. Now, we calculate the J integral, still in polar coordinate, and we consider as a counterclockwise integration path a semicircle centered in the right corner, which starts from below the punch and ends in the free surface. And then we push the limit for the radius of the release rate associated to horizontal growth of the punch. And what we find out? We find out that these two quantities are the same, are the identical value, and they differ by a coefficient -2 from the energy release rate and the J integral that we have in mode 1 crack propagation. But according to the regional inclusion, this value is never positive. It's always non-positive. Considering now the case in which our flat rigid punch is indented by a vertical force P, is well known the expression of the pressure distribution that arises below the punch. So we can now specify the expression of the stress intensity factor K1, and now we can plug this identity for K1 in the expression for the J integral. But what happened when the corner of the punch are not sharp anymore, but they are rounded? And the first derivative of the equation which describes the geometry of the punch is reported here, where A represents the limit in which the punch is perfectly horizontal and flat, while B is the unknown point in which we lose the contact between the elastic medium and the punch, and R is the radius of curvature of the smoothed corner. Now we introduce a map for the horizontal coordinate x1 in function of the variable, the parameter phi, and following Chavarella is reported here also the vertical component of the contact pressure distribution. And now we have all the ingredients. We know the vertical component of the contact distribution. We know also the geometry of the punch, so we can try now to calculate the horizontal contact reaction force. So what we do, we perform the integral from A to B of the horizontal projection of the vertical component contact distribution, and we are not surprised that this integral is always positive. But what happened when the corner of the punch coming back to be sharp? We can try to push the limit for B that tends to A, and we find out that this limit exists, is finite, and is equal to the minus the J integral, minus the energy release rate. So what we can conclude? We can conclude that even if the J integral was already investigated in indentation problem in linear elasticity, it was never related to the energy release rate associated to an horizontal growth of the punch, but on the top of that, it was never related to the horizontal component of the contact reaction force. And these results, this non-accidental coincidence, invite us to study this concept also in nonlinear regime. But before to do that, let me do a very brief overview about finite elasticity. So let us consider an elastic body embedded in a three-dimensional Euclidean space, and let us consider two configurations for this body. B0, the reference position, to one point of this body, which in the reference configuration is x0, but in the current configuration is mapped in x. So now we can define the displacement vector u at x minus x0. We can also define the deformation gradient as the gradient of the just defined vector u plus the identity, and assuming also assuming now hyperelastic response, the Kirchhoff stress tensor is equal to the first derivative of the strain energy density function with respect to the deformation gradient. We can also relate first Piola to Cauchy by using the deformation gradient and its determinant. And in absence of body forces, the equilibrium equation simplified in the just requirement of first Piola is solenoidal. In other words, is divergent free. Introducing now the concept of frictionless contact, we consider two bodies. The target body, the rigid one, and the conductor body, the deformable one, which in the undeformed configuration, they are not in touch, but in the current configuration, they are. And let us now define three different regions of this body. Namely, we have delta V touch, which is the portion which is actually in touch with the conductor, delta V sigma, where we impose the stresses, and delta V u, where we impose the motion. And now we define frictionless contact, the condition in which the traction vector is always orthogonal to the tangent. And now with the well-known pullback operation, we can write this equation, which is here expressed in the correct configuration. We can, by using the pullback operation, we can move this identity in the reference configuration. And by using the definition of the deformation gradient, we can obtain this third and last equation. Talking again about the Eshelby energy momentum tensor P, now defined at the finite strain, in total analogy with the one that I show you in the linear elasticity, it is in function of the strain energy density function and gradient. But at finite strain, we have to substitute the Cauchy stress tensor with the first Piola. It's possible to demonstrate, and I'm not going to do it now, that the Eshelby energy momentum tensor is solenoidal, is divergence free. And by using the divergence theorem, we can move this property in integral form. So we require that the integral along the boundary of the first Piola Kirchhoff stress tensor is equal to 0. Now we can use the Eshelby energy momentum tensor to calculate action force R1. So let us consider an elastic domain subjected to pressure distribution, a frictionless contact. And since we want the horizontal direction, the solenoidal property of it. And now we split the integration along the boundary, along the integration along the only vertical and horizontal edges, where on the left-hand side we have the integration along the horizontal and delta PB of the Eshelby energy moment. Simplified in the now we split again the integration along the only delta BA and delta BB, so we can clearly identify now that this is the total reaction force along the horizontal edges delta BA and delta BB. So what we can conclude that the total reaction force R1 is equal to minus the horizontal projection of the integration along left and right of the Eshelby energy momentum tensor. Going further, we can now introduce the definition of P, obtaining this tensorial equation, and now we can express this tensor by the component, obtaining now this equation. Assuming now that along left and right, we are in absence of shear stresses, and in one, it's equal to a dead load or some constraint reaction applied to the only left or right edges. Conclude. The R1 is evaluated in the left minus the right edges over the horizontal stretch performed on the constraint fiber times the undeformed height of the solid. So what this equation is communicating to us, that R1 is in function of only the first and the last fiber, nothing else. Generally speaking, so in considering now a generic surface, any surface in frictionless contact with our R1 performed along a portion in contact delta p touch is of course equal to the horizontal projection of the integration of the first Viola Kirchhoff stress tensor integrated along delta p touch. But we demonstrate that is equal also to the integration of the first Viola Kirchhoff stress tensor along delta p touch. But we demonstrated that is also equal to minus the integration of first Viola all around the other part of the boundary, so excluding the portion in touch. But this is exactly the definition of J integral. So what we can conclude? We can conclude that with demonstration force. The second section of my study is devoted to investigating the relation between the horizontal component R1 and the going to consider an elastic body indented by a frictionless flat rigid punch with a sharp corner. We are going to consider a domain of the elastic body containing the singularity. So our corner, sharp corner, in the undeformed but also the format configuration. We want to simulate an horizontal of the punch. We are going now to consider a second subdomain, which is exactly the same one, but shifted by an infinitesimal amount to the left in the undeformed, but of course in the formal configuration. Why? Because we expect a configurational forces arising in the corner. And we are going to compare the change in the total potential energy of this subdomain because we want to connect this configurational force with the energy release rate, and as a consequence to the J integral. So here are the top, we are as the is in the formal configuration, and on the right is in the formal configuration. And we are going to consider in the original scheme a subdomain containing the singularity. While the two sketches on the bottom are labeled replica. Why replica? Because in the undeformed configuration, the subdomain who contains the singularity is the same, but is a replica because it is the same subdomain, but shift amount to the left. We are going to proceed, and we perform the difference. We perfect the difference from the replica to the original. To move ahead the singularity, now we try to plug the replica subdomain in the hole left free by the one. And if this operation is trivial in the deformed configuration, is not so trivial in the deformed configuration because the hole left free by the original subdomain has got the same shape of the replica subdomain. So we have to consider an extra work in order to change the shape of the hole, and now the subdomain can perfectly fit. And here is reported the amount of work necessary to move the boundary of the original subdomain. Now the body is restored, and as you can see, the singularity is moved ahead. And now we can finally evaluate Thank you. It's going. It's not changing slide. I don't know.
I lost focus. Try to separate.
What I have to do?
Focus better. Enter the slides there.
Okay, thank you. Where I was, okay. So let us now consider our elastic body constrained by two rigid punches. And now the punches are fixed, they don't move anymore because now we have to replicate an elastic rod constrained by sliding slip. And according to the assumption usually made in rod kinematics, our elastic body is this deformation equation, where U.
Sorry, the presentation is not shared yet. But sorry, I'll sip of water.
Is the rotation, but these three kinematics fields are not independent because we want our elastic rod to be unshareable. So we impose. Non cambia slide. Please not change the slide, sorry. This is morale. Okay. Yeah. Okay. Thank you. Thank you very much. So the three kinematics fields are not independent because we want our rod to be unshareable, and so we impose the Euler-Bernoulli constraint. So any cross section should stay to the beam center line. But since we want our beam to be axial extensible, here we have the axial deformation equation. And now we try to calculate the configurational force in this particular setup by using the Escherby energy momentum tensor P. So since we know from Bigoni studies that the configurational force arises at the sliding slip axis, we select for the left and right material fiber the cross section which is just after and just before the sliding slip axis. So now we perform the integration along the cross section, obtaining this identity for the configurational force, where the pair of square brackets represent a jump in the quantity. So we are going to have a jump in the elastic energy, a jump in the elastic force, and then the bending moment contribution. Assuming now a quadratic strain energy, where B is the bending stiffness and K is the axial stiffness, considering also the constitutive equation for the axial force and the bending moment, the configurational force simplify as follows. And pushing now the limit for the inextensible case, we are able to find out the same equation that Bigoni had this group find out back in the days. Now we are going to apply all this huge corpus of equation to two boundary value problems. First of all, we have to assign a material response. So we're starting from the material model proposed by Storakers for compressible materials and materials which are also initially isotropic. And yet propose this material model by a series of terms. We test. So we can give an interpretation to the parameter. As an example, mu is the ground state shear moduli alpha the nonlinear response affect the compressible response. In the particular case in which alpha is equal to 2, we have the Pensier-Go material model, which is nothing else than a compressible interpretation of the incompressible neo-Hawkian that we can obtain by pushing beta to infinity. Here, I reported our two boundary value problem examined. On the top, we have BVP1, on the bottom, BVP2, which consists in an elastic block indented by a rigid punch and constrained, both of them, on the bottom with a set of rollers. And for BVP1, we have a set of rollers also on the left edges, while for BVP2, the rollers are on the right. I reported also the identity we derived for R1, so the difference in the strain energy function evaluated in the left minus the right edges over the horizontal stretch evaluated in the constrained fiber times the deformed height of the solid. And when we assume a compressible response for our solution in closed form, so this is why I reported R1 as a series expansion. But we can have a closed form solution when the incompressible response is taken into account. In these two plots, we have the behavior of R1. So focusing our attention on the left, okay? On the vertical axis, we have the normalized R1 in function of what? In function of the vertical stretch below the punch. So what we can see that our force R1 increase while increasing the deformation. So the vertical stretch below the punch. While on the plot on the right, we have still normalized R1 in function of the Poisson ratio. So basically, we can get our maximum R1 when our body is incompressible, let's say. And in continuous line, these are the semi-analytical result for BVP1 in continuous line, but the behavior is exactly the same when we consider BVP2 dashed line, still increasing the Poisson ratio. Now, let us go into validate by finite element our R1 for BVP1. Here is reported as an example where, can you see the contour plotter is a bit messy. It's a bit messy, I guess. I don't know from your point of view, but this is a contour plot in which we report the error, the relative difference between the semi-analytical and the finite element R1, where on the horizontal axis here we have L in over L0, which is a parameter which defines inside the constraint when compared to the undeformed length of the sample. While in the vertical axis we have R over H0, which is a parameter which describes the incidence of the radius of curvature of the punch when compared to the undeformed height of the solid. This error map, I don't know if you can see it, but please trust me, basically says that the relative difference is basically 0 all over the map. But so the numerical approach and the semi-analytical approach are in very strong agreement. But our theory starts having some problem when we consider the two limit cases. So the cases in which our solid, our sample, is basically almost inside the constraint or outside the constraint. In this slide, we have an animation extracted by the finite element simulation, where the line in blue is the semi-analytical solution. And as you can see, the numerical one, the red one, is basically overlapping the blue line. Let us now apply our problem in two particular cases. The first one in two particular applications. The first one is the Eulerian buckling. So we consider now our elastic body compressed by rigid punch at both ends. And thanks to the symmetry of the problem, we can recognize our BVP2. And we start compressing. And so we ask ourselves, but is possible to find a critical value of this compression that can induce Eulerian style buckling like in the road case? And to answer to this question, we brought here the equation, the equilibrium equation for a variable length, axial extensible, unshearable, elastic rod, constrained by, at both ends by sliding sleeve. Then we introduce a small perturbation in the rotation and the axial deformation, and we linearize the equation. And so we can find a non-trivial solution for R1. And now we compare this R1, the critical load, with the R1 for BDP2. So we can find here the critical stretch expanded in series that can lead Eulerian style buckling. Again, what we've done, we have considered an elastic body compressed at both ends by the rigid punch. We start compressing. We are still below the critical value, but when the critical value is reached, our body buckle exactly the same way which buckled the elastic rod. And here is reported in blue the semi-analytical result, where in the vertical axis we have the critical stretch, and in the horizontal axis we have the slenderness ratio, D over H0, where D is the distance between the rigid punch and H0 is the undeformed height of the solid. And let us now compare this semi-analytical result with the finite element one, and again, we have a very good agreement between the two approaches. Here is reported an animation by the finite element simulation. When the critical stretch is reached, our body slips out from the constraint. The last application is the dynamic ejection. So we demonstrated that when an elastic body is compressed by the rigid punch, a configurational force arises in the corner of the punch. And this configurational force is in equilibrium with a constraint reaction. So now we ask, but if we remove the set of roller equilibrium, and our body should be ejected from the compressive state. And now, so we ask ourselves if we can predict the ejection process that we set to assumption. And the first one is that the R1, our reaction force, stay constant in time all along the ejection process. And the second assumption, we basically simplify the deformed shape of our body into blocks. One block inside the constraint and one block outside. And we focus all the mass of the sample in the center of mass of the two blocks. So we can now write the Newton's second law for the center of mass of our body, where the location in time is represented by this equation. So the second order differential equation takes this shape in the unknown function L in of t, which represents the amount of material inside the constraint, and these two are our initial condition. So our body, when t is equal to 0, the velocity is equal to 0. And in the initial condition, we suppose to know how much material is inside the constraint. This differential problem allows for a closed form for L in, and since we know L in t, we can also predict the time of the complete ejection. Here we are, the perfectly analytical, not semi-analytical result, where in the horizontal axis we have the non-dimensional time, and in the vertical axis we have the normalized L in of t. And comparing now this analytical result with the numerical one, we have a very strong agreement between the two approaches. The same is for the relative difference in the time for the complete ejection. In these 4 snapshots of the ejection process, we have reported 2 contour plots inside the elastic body. The contour plot on the top is representing the kinetic energy density, while the contour plot on the bottom is reporting the strain energy density. And this 4 snapshot is basically communicating to us that our assumption of 2 blocks is acceptable. Why? Because the contour plots are basically uniform inside and outside the constraint if we neglect a very small and localized region of perturbation aligned with the sliding sleeve exit. Again, we have a finite element animotion where the blue line is the analytical result and the red line is the numerical one. And the two curves are very, very, very close. To conclude, by a frictionless flat rigid punch, a configurational force arises in the corner, and this configurational force is shown to be equal to the energy release rate associated to an horizontal growth of the punch. It's also equal to the J integral performed around the corner, but on the top of that is equal to minus the horizontal component of the contact reaction force. This configurational force can induce Eulerian style buckling, and last but not least, we was able to thanks for your attention.